4.10, antiderivatives and what are called indefinite integrals. So we're trying to move forward into 5.3, where we can speak about the fundamental theorem of calculus, and that will be more easily explained if we have an idea of what's called an antiderivative. So in 4.10, that's what's talked about. Right now, capital F prime of x is f of x. Okay? So if you have a relationship like this where the derivative of one function is another, and this is a common notation, that capital F, when you take its derivative, you'll get a lowercase f. That's a common way to describe the relationship between these two. If this is the case, then capital F without the derivative is an antiderivative of little f. Okay? So the relationship is, if I take the derivative of one and I get the other, then that means the first one is an antiderivative of the latter. Okay? And there's a special notation to denote this, and that's where the idea of indefinite integral comes in. Another way to write this is the integral of f of x dx is cap fx. Sorry, I don't need the derivative symbol there. Okay. You'll note that there's no limits of integration. There's nothing to do with areas per se. We're not calculating an area in this regard. We're now looking at the integral symbol, right? So this symbol now, the integral symbol with the dx, only means this is equivalent to take antiderivative of the integrand. Whatever you find inside, take its antiderivative. That is, find a function whose derivative is the integrand. Right? So these are now considered inverse processes. Right? If the derivative of one is the other, then the antiderivative of the latter is the former. Right? So you can think of the integral symbol with the dx as being the opposite operation of the tick mark or ddx symbol. Okay? So therefore it's antiderivative. Let's take a small example. So let's say we want to find the antiderivative of 2x. Okay. There we go. I want to apply the antiderivative operation, you might think of it that way, antiderivative operation to 2x. Well, we know that if we take the derivative of x squared, we get 2x. So therefore, x squared is an answer to this setup. Right? So the antiderivative of 2x is x squared because the derivative of x squared is 2x. But we also know that when you take the derivative of a constant, it goes to 0. So therefore, to write this out in its most general way, I'm going to write plus c here, plus any arbitrary constant. Okay. So this is called the general antiderivative. Because it incorporates all possible answers, right? Because the derivative of x squared plus 1 is 2x. The derivative of x squared plus 2 is 2x. The derivative of x squared plus pi is 2x. The derivative of x squared plus e is 2x. Right? It doesn't matter what value c would take on, the derivative of the right-hand side would be the integrand. Therefore, these are all possible answers. Right? Just leave c arbitrary, don't pick a particular value. And this will be the general solution to this type of scenario. Another example. Integral of e to the x dx. Okay? So I want to find the antiderivative of e to the x, but we know that the derivative of e to the x is e to the x, so therefore it must also be its antiderivative. Okay? And I'll just put plus c to complete having the general antiderivative here of the e to the x function.